because that's kind of different in terms of luminosity, no? So yeah, let's welcome our next speaker, yeah?
Yes, thank you very much. Thank you very much for the invitation and for the introduction. Can you hear me? Yes? Okay, so I'm sorry first that it seems the virtual background doesn't work for me. So, okay, so I will just use my Blackboard as a background. And so I'm going to talk about searching for the dark side of the universe with help from the sun. But this is supposed to be a short review, but it'll be highly biased on my own work. Okay, so okay, now let's start. Okay, so basically we know that the dark matter exists, right? Just from observations on different scales, from the all the way from the smallest, from the rotation curve of the galaxy, and all the way to the CMB, which is CMB background, which is the whole universe. And from all the informations, we just construct the decomposition of our universe. So basically, we have 30. We know that the standard model of particle physics only predict so the particles in the standard model of particle physics only consist of about 4% of the total energy density of our universe, and about a quarter, which is unknown, is called dark matter, and the other 3/4 is about which is also unknown, is called the dark energy, right? So we know that dark matter exists, but only from the gravitational effect, right? So what we already know, so that the dark matter is a matter-like, right? Matter-like means it is a thing, right? It is not part of the theory itself. So as a particle physicist, we want to assume that the dark matter is composed by new particles, right? And so basically what we want to know is its particle nature. So in detail, what we want to know is mass, spin, size, internal structures, or interactions with standard model particles other than gravity, or or if it has any self-interaction other than gravity, right? And so these are since Kaixuan already gave a very nice talk about xenon detector, and so basically, right now for about 30 years, even longer. So most of our effort to search for particle nature of dark matter are based on nuclear recoils, right? And so basically we have two kinds of detectors. So one is the noble gas detector, so just like xenon, lux, and panda X. And the other kind of detectors is like using semiconductor technology, which is the famous CDMS detector, and this is CDX detector, leading by Tsinghua University. And so basically, so for the noble gas detector, it actually can be easily to build large, right? We already have xenon n-ton, and for this semiconductor detectors, it is not very easy to build a large detector, but the threshold can be small, right? So that it is better for semiconductor detector, it is better to search for light dark matters for mass around 1 GeV. But for noble gas detector, it is easy to go smaller cross sections, but with a larger mass. Okay. However, the theories are clever, right? So basically, during these times, so the theories have built just a lot of dark matter models. And in each model, it is possible to introduce some kind of Z2 symmetry or U1 symmetry. So in order to have a dark matter, right? Or even very long-lived particles to have dark matter candidates. And this is this plot is actually drawn by Tim Tate many years ago. And I think about at least 7 years ago. And in these 7 years, there are more dark matter models just proposed by series, right? So basically, we have a lot of models, and the mass range of dark matter particle in all these models just can have a very large range, all the way from this 10 to the minus 31 GeV, all the way to so this is called fuzzy dark matter, and all the way to the about 10 to the 50 GeV, which is the primordial black holes, right? So in such a large mass range, so the direct detection experiments, something like xenon or xenon-like, so noble gas-like, or this CDX-like experiment. So the condensed matter this semiconductor-based experiments only cover a very tiny region in this whole mass range, right? So how to search, for example, this region, right, for the MeV scale thermal dark matter, or even lighter dark matter, or even heavier dark matter, it is still a problem, and it's challenges for people to think about new ideas, right, to search, okay? And so basically, so today I'm going to talk about how to use the sun to help us to search for these dark matters. So for search for dark matters in this mass range, for example, the MeV scale thermal dark matter and the axion or dark photon dark matter. So today I'm going to focus on dark photon dark matter because Kai-Chuan has already talked a lot about this axion dark matter and direct detection of axion dark matter. Okay, so to use stars as laboratories for fundamental physics has been started for a long time. I think about 30 years, right? And there's actually a very nice book by Professor Raffelt, and this is yes, and from there can learn a lot of detailed information about stars and how to use stars to search for light particles. So basically, the stars we have first the sun, right, which is the closest to us, and the next to the sun is the right giant stars or horizontal branch stars. And the difference is that the energy of the core of these right giants or horizontal branch stars can be orders of magnitude larger than the temperature at the core of the sun, right? So basically at the core of the sun, we know the temperature is about 1 keV, but at the center of right giants or horizontal branching stars, the temperature is about 10 to 100 keV, right? So it's 10 times or 100 times larger. And also neutron stars. So neutron stars recently becomes interesting to particle physicists. That's because neutron stars has a very large magnetic field, right? And so the photon, for example, if axions dark matter candidate, so inside the large magnetic field, the axions can be converted into photons and can be detected. And also supernova. So the advantage for supernova is because its energy at the core is even larger, can achieve 20 to 30 MeV. And the next one is even more extreme stars, which is the black hole, right? And in black hole, people can study super radiance effect and can study even the lighter, it's more sensitive to very light axions, so bosonic dark matters. Okay, so today I'm going to focus on the sun. So this is the outline of my talk. So first I will give a very brief introduction of the basic structure of the sun. And then I'm going to talk about how to use the sun to search for MeV scale thermal dark matter. And so basically the MeV thermal dark matter can be accelerated inside the sun. And next, I'm going to talk about how to search for dark photon dark matters inside the sun. So basically, there are two things the sun can help us. So basically, one of them is that if the dark photon is lighter than about 1 keV, it can be copiously produced at the core of the sun, and then it can lead to some observable effects. And also, if the dark photon is very light, if the mass of dark photon is at a radio frequency, right? So something like 10 to the minus 6 eV, okay? Then I will show that it can be converted into photon at the surface of the sun, and then the photon can fly onto the surface of Earth and be detected. And then I will summarize, okay? So here, let's first have some basic idea about the about structure of the sun, okay? So what is important for us? So because we want to produce the dark matter particle inside the sun or accelerate the dark matter particle inside the sun, right? So the most important thing is the temperature. So basically it's the energy of the electrons inside the sun, which is the most important. Okay, so here this plot shows the energy distribution. So at the center, so the x-axis is the radius, is the radial position of the sun, and the y-axis is the temperature. We can see that the sun has a core, which is in the radial size is about 10% of the radius of the sun, and the temperature is about just 1 keV. Okay, so that means it is proper to accelerate the dark matter particle to 1 keV, or it can produce 1 keV dark matter. And this 1 keV, as Kai-Chuan said, right, is already past the threshold of electron recoil at like xenon detectors. Okay, so and also as I mentioned earlier, this not only the inner structure of the sun, the surface structure of the sun is also important. The surface of the sun composed of in the inner region there's a chromosphere, there's also a photosphere and chromosphere, and also the corona. Okay, it's like this. So the purple curve, the purple dashed curve here shows the temperature distribution. Okay, and this is the temperature. So basically at the at the surface of the sun, the temperature is about here, okay? It's about 6,000 Kelvin, okay? However, once we go above, once we go higher and higher in the sun's atmosphere, okay? And once we reach the chronosphere, the temperature actually gets higher, okay? Gets higher all the way up to 10 to the 6 Kelvin. 10 to the 6 Kelvin is about 100 eV, okay? And the mechanism for this, for why the temperature of the corona is much higher than the temperature of the chromosphere is still unknown, okay? But this is the fact. So basically people can measure the temperature because it's already outside the sun, right? And the people can also measure the electron density outside at the sun's atmosphere. Okay, so basically you can see, what you can see here is that with the larger radius, it drops very fast. Okay, and this is actually very crucial for the dark photon search. I will talk about that later. Okay, so how to search for this region? So that's just the first move, one small step smaller, right? In this plot, let's first focus on this MeV scale dark matter, or how to do this search. Okay, so basically, because if the dark matter is like MeV scale, then the kinetic energy is only about EV scale, right? Only about EV, which is lower than the threshold of most of the experiments. Okay, so the first thing in our mind is the following, right? So because in this kind of dark matter, it can, so usually in the experiment, what we search for is the recoil energy, right? And so just from high school physics, we know that the recoil energy is related to the kinetic energy of dark matter and the mass of the dark matter and the mass of the target particle in this way. Okay, so basically you can see to transfer the largest kinetic energy from the dark matter particle into the target particle, what we need is the target mass roughly the same as the mass of dark matter. Okay, so basically for MeV scale dark matter, we can no longer use the nuclear recoil. What we should look for is the electron recoil, right? And so people already consider this, and this is the result of the Xenon one-ton S2 only analysis, right? In last year, okay, last year. And so basically what you can see is that for dark matter mass roughly larger than about 10 MeV, it can give actually very nice constraint, right? Can give a very nice constraint. Okay, so but what about if the dark matter mass is smaller than about 10 MeV, right? What shall we do? Okay, one thing is to, of course, lower the threshold of the experiment, right? This is always people wants to do, right? But it is difficult. So how to lower the threshold? So basically we can use semiconductor detector or superconductor detector, but this is still a concept. And there's another technology which is, this is also the semiconductor detector, but using the so-called skipper CCD technology. And the people also propose to use a nanotube to search for light dark matter. And the other strategy is so what I want to emphasize in later talk. So it's to accelerate dark matter particles. Okay, so let's first talk about this skipper CCD technology. There's already this is already ongoing experiment, and it's already published some results, very nice results actually. So basically, using this technology, they can show that they can lower the electron recoil threshold to about 1.2 eV. Okay, and this is already about 1 order of magnitude smaller than the threshold electron recoil threshold of Xenon experiment. So that we know that the first excited, the first ionization energy of the Xenon atom is about 11 eV, right? So this is about 1 order magnitude smaller. And so this will be sensitive to dark matter with a mass about with a mass larger than about 5.5 MeV. So basically electron mass, that is here, okay? But you can already see that at this threshold, the constraint is already, the sensitivity is already not very good, okay? And for absorption, right? If the dark matter can be like axions or dark photons can be absorbed by this by the atoms, right? Then the threshold for the mass of dark matter can be as low as 1.2 eV. This is amazing, right? But what if the mass of dark matter is smaller than this? Okay, so what can we do? For example, smaller than about a few MeV, right? So we can use this idea, right? This is our idea. So basically, the dark matter can first fly into the sun. So a part of dark matter can always, this can always happen, right? For part of the dark matter particles, they can first fly inside the sun. And because the temperature at the center of the sun is about 1 keV, and if this dark matter can be kicked by the electrons at the center, at the core of the sun, right? Then its energy can be at least become kinetic energy, can be accelerated to about 100 eV, right? And then from the sun, it can just fly back to the surface of Earth and then fly into this dark matter detectors, and either xenon detector or this condensed matter semiconductor detectors, right? And then can be detected. So we just did this analysis. So, but first, because this part of dark matter needs to fly into the sun first, and then fly back to Earth, and then fly to the surface of Earth, right? So we know that there must be a penalty because the sun is actually not very close to Earth, right? So then we should pay this. This is the penalty of the flux we should pay. So basically, it's a pi r sun squared. This is the radius of the sun, and this d is the distance between the sun and the Earth. Okay, and so this factor is about 10 to the minus 5. So this means that, so compared to the direct search for the dark matter from the halo, using this mechanism, right? Using this method, so there's a penalty about 10 to the minus 5. Okay, factor 10 to the minus 5 smaller. However, there's another effect. That is because the gravity of the sun, right, is relatively large, so that the dark matter particle does not travel like in straight line, right? So basically, we know that it is something like a parabolic curve. Okay, and so there's a focusing effect. Just using the high school physics, we know using the high school physics of the kinetic energy conservation and the angular momentum conservation, we can roughly calculate that this focusing effect can be written in this factor. And this is about, so given that there's a the escape velocity of the sun, right? So we know that the focusing effect can be about a factor of 10, right? So basically the total penalty, once we combine these two numbers together, is about 10 to the minus 4, okay? And so we did a numerical simulation. And so the spectrum, the normalized spectrum of the reflected dark matter is like this. So the spectrum composed of two parts. The first part, this part, at the small energy region is still the halo part. That means this part dark matter, although they travel inside the sun, but they didn't get accelerated. They just go through the sun and then just get back to Earth, right? And then this just from here, this part of the spectrum is the accelerated spectrum. And we can see that, so of course, with the larger cross section, this part just becomes bigger, right? The accelerated part becomes bigger. However, if the cross section is too large, for example, if the dark matter electron cross section is about 10 to the minus 33, then we can see that we can see that the dark matter just have a lot of scatterings inside the sun, and then it is very hard for the dark matter particle to reach the core of the sun, right? So one can see the result is that for larger cross sections, the spectrum, although the plateau is higher, but in general the spectrum is softer. Okay, and for smaller cross section, the spectrum is actually harder. And so we apply this. So using this simulation, we can generate the reflected flux, and then we use the reflected flux. We can calculate the constraint from this dark matter direct detection experiment, because this is already past the threshold of the S2 signal, right? The electron recoil signal. And so this is our result. So like in 2018 we did this work, and this is the result. And you can see what you can see that is in this region, so around 1 MeV, smaller for dark matter mass smaller than about 1 MeV, right? And so basically we can get a constraint, and this region basically cannot be explored by previous result, by directly searching for dark matter in the halo. Okay, and so this curve. So why this region is interesting, right? For such a small mass, why is it interesting? Can this dark matter be produced? Yes, it can, right? So basically, we did some study basically for this gray curve. Okay, for this gray curve is indicating that there's dark matter, the dark matter with this mass range, and so they can can produce the thermal radical abundance, today's observed thermal radical abundance through thermal annihilation, okay, just like a WIMP dark matter. And I forgot to say that for this spectrum, for the simulation of this spectrum, so basically we assume that this is S-wave only scattering. So we assume it's contact interaction, and and the interaction is momentum independent. Okay. And so compared with the Sensei result, what we can see that, so it's very nice that in the most recent Sensei paper, they also put our constraint on it, our curve on it. You can see that this is from the constraint of our consideration using this Zenon-Wang result, but this is not the latest Zenon-Wang result. And you can see this is our constraint, and it is quite complementary to the Sensei result. Okay. Yeah. So, and so in our in the work I presented, so we assumed that the interaction between dark matter particle and the electrons is a S-wave contact interaction, right? And we know that it can be, so we can, in principle, we can also include some form factors, right? For example, in one very well motivated case, that is a very light mediator. The very light mediator case, I think Kai-Xuan also showed this plot, which is the dark matter interacting with the electrons through a dark photon portal, right? Basically, the dark photon has a kinetic mixing with our photon, right? And in this interaction, the dark matter particles can actually be produced through the freezing scenario. What is freezing scenario? So freezing scenario assumes that that after inflation, only our standard model sector gets reheated, and there's a very small portal, very small interaction between the dark sector and the standard model sector. And through this very weak portal, the energy density of the standard model sector just slowly leaked into the dark matter sector. Okay. However, the collision between the dark matter particle and the electrons happened inside the sun, right? And we know that the sun, inside the sun, is no vacuum. Okay, it is a thermal plasma, and that means to calculate this process, we must consider a plasma effect of this photon propagator, right? So basically, we need to consider all these diagrams, and if once we sum all these diagrams together, what we get is a double screening effect, right? As we already can imagine. However, because in our case, the dark matter particle actually kicked by the electrons, right? That means there's a sizable momentum transfer we should expect. Of course, we want this momentum transfer to accelerate the dark matter particles, right? So what we should deal with is a momentum-dependent double screening effect. And turns out it is very difficult to do the simulation. But somehow we feel like that we already find a good method to do the simulation, and the work will be published maybe in early next year. Okay. And so what we can also do is the following, that so the dark matter can actually have something like an excited state, right? So for example, if we imagine so there's a very small gap, so the dark matter is very close to another dark matter particle, and the gap is about in the range of 1 keV. And this is people already consider this scenario in light of the recent Zenon-Wang access. And so basically, this dark matter particle can fly into the sun and be excited by electrons inside the sun, and then fly back to the Earth and de-excited. Okay, and then this gap energy just can be released, and then this gap energy can just cause something like a keV scale electron recoil, and then produce the Zenon signal. And in this paper, they presented this idea. Of course, we had this idea like last year, right? But somehow we haven't finished this simulation, and then suddenly the Zenon result just came out. So yeah, so maybe already, since we already have the tool, maybe we just do a detailed simulation to see how good this can work. Okay, so now let's turn to the dark photon dark matter. Okay, so let's talk about how the sun can help us to search for dark photons. So first of all, what is the dark photon, right? So I also mentioned the dark photon earlier in this talk, but what really it is? It is just a new vector boson and coupled to the standard model particles only through the kinetic mixing with the electromagnetic field with our photon. Okay, like this. So basically, it's a its kinetic term is the same as the photon, and it couples to our photon through kinetic mixing. And because we want it to be a dark matter candidate, so then we also should assume that there's a mass term here. Okay, there's a mass term here because without mass, it can never be dark matter. Okay, and the mass can be generated into two mechanisms. One is the so-called the Stueckelberg mechanism, and so you just write down a mass term, or you assume the Higgs is very heavy, decouple it, right? And then in the effective Lagrangian, you only have this term. This is usually called Stueckelberg mass. And the other case is usually called the Higgs case. That is usually we assume there's a Higgs. There's also a Higgs particle which is as light as this dark photon. Okay, and so then the Lagrangian should also have this piece, right? No, so in order to have this interaction, it must have also have the interaction with the Higgs and also this 4-point interaction. And it turns out that this in the Higgs case, this part of the interaction is crucial for the production inside the thermal plasma. Okay, and then how to produce the dark matter, dark photon dark matter in the early universe, right? There are people already proposed several mechanisms. For example, in this work, the authors propose that the longitudinal mode of the dark photon dark matter can be produced during inflation, and they show that in this way they can produce the today's observed radical abundance. And also in these papers, suddenly I think all these papers came out in one day, right? They all propose to use a parametric resonant decay of a scalar field or scalar oscillation of a scalar field to produce a dark photon dark matter. And also recently, people proposed to use a misalignment, of course, with a non-minimal coupling to the gravity to produce dark photon dark matter. So basically, dark photon dark matter is a well-motivated model, and it can. So we do have mechanism to produce it in the early universe. Okay, and now how to search for it, right? So first, just as I talked earlier, so we can produce it copiously inside at the core of the sun if its mass is smaller than 1 keV. Okay, so now let's see how, and then the production of dark photon can lead to three observational effects. So first of all, it will take more energy, right? It will take more energy directly from the core of the sun, right? And then that will accelerate the burning of the sun, and then it will influence the sun's lifetime. Okay. And secondly, it will change the temperature at the core of the sun, okay? And thus, it will change the solar neutrino flux. It turns out the boron 8 neutrino flux is very sensitive to the temperature at the core of the sun, okay? And we know that the flux of the boron 8 neutrinos already observed by Snow experiment, right? And so this can give a very stringent constraint, basically saying that the constraint from boron 8 neutrino is that the dark luminosity of the sun should be smaller than 10% of the luminosity of the sun. Okay, and another way another signal is that the keV scale dark photon can emitted at the core of the sun can fly all the way to the dark matter detectors, right? And since its energy is already larger than the threshold, it can generate a signal, right? An electron recoil signal, and it can be detected. Okay, so how to produce the dark matter inside the sun? Okay, it's actually a tricky process, but there are two main very important production channels, which I'm going to talk about, right? So basically, once we saw this interaction, so basically this is a mixing between the dark photon and the photon, right? Once you see a mixing, you'll know that in some condition, the photon can just oscillate into dark photon, right? But we know that this cannot happen. This cannot happen in the vacuum. Why is that? It's because the photon and dark photon in the vacuum have different dispersion relations, right? For oscillation to happen, we must match the full momentum, right? But if the dispersion relations are different, then we can never match the full momentum, right? So this cannot happen in the vacuum. However, in a thermal plasma, the things become different because the photon got an effective mass. Okay, so basically, in a non-relativistic plasma, just in the in the sun, right? Because the kinetic energy, the temperature already, although it's 1 keV, right? It is much smaller than the mass of the electron. So it is a non-relativistic plasma, and the dispersion relation of the photon can be the transverse part of the photon can be written this way. Okay, and for dark photon, it is like this. Okay, so then now we can match them. Okay, so basically once the mass of the dark photon is equal to the plasma frequency of the plasma, right, then we know that the resonant transition can just happen. So the photon can just oscillate into dark photon. Okay, and then the dark photon can fly outside the sun and then be detected. Okay, but this is only for the transverse photon. We know that in the plasma there's actually a longitudinal mode of the photon, right? But the longitudinal mode is actually composed by the collective local oscillation of the electrons around the ions. Okay, so this is in the plasma, and the dispersion relation of the longitudinal dark photon is still the same, right? It is still the same. However, for the photon, it is different because it is only a local oscillation without any propagation, right? So the dispersion relation for the longitudinal photon can be written as just simply in this way. So omega equal to the plasma frequency, omega p. And now to match the two conditions, it is actually easier, okay? So to match the formal momentum, what we just need is omega equal to omega p. But to have a real momentum, right? So the energy momentum must be larger, the energy omega must be larger than the mass of the dark photon. Okay, so this is the only condition. So the condition is, so you combine these two together. That means for the longitudinal dark photon to be produced resonantly, right? So what we need is the omega p larger than the mass of the dark photon. Okay, and so as you can see that so in this analysis, the plasma frequency becomes very important, right? And so this plot shows the distribution of the plasma frequency inside the sun. Okay, so this is at the center, and this is the surface. And so basically at the center, so the plasma frequency is about 300 eV, and at the surface of the sun, it is about 1 eV. Okay, and so basically for omega p, for basically if the so there's a typo here, sorry. So this omega p should be replaced by the dark photon mass. So for dark photon mass between 1 eV and 300 eV, that means both the longitudinal and the transverse modes can be resonantly produced. And if the omega p is smaller than, if the dark photon mass is smaller than 1 eV, okay, then only the longitudinal modes can be resonantly produced. And if the dark photon mass is larger than 300 eV, then there's no resonant production at all. Okay, and so basically we applied this analysis, and then we calculate the flux, and we calculate the constraints from this conditions. We calculate the constraints from this boron neutrino constraint, and also from the xenon experiments. So basically, this is the result. So we just updated the result very recently. So yes, in light of the xenon access. So basically, this is the current result. So the blue curve shows the gray region is actually excluded by the boron 8 neutrino consideration, and this blue curve is excluded by the xenon 10 result, and this is the new xenon 1-ton result. This red curve. The xenon 1-ton S2 only analysis, through the xenon 1-ton S2 only analysis. Basically, it's the last year's paper. And okay, so what you may wonder is that what are these horizontal curves, right? So the horizontal curves are actually for the Higgsed case, okay? And these curves are actually, these solid curves are actually from the Stueckelberg case. So, and you may also wonder why for lighter dark photon, the constraint becomes there's a less constraint, okay? Why there's a less constraint for lighter dark photon? That usually doesn't make any sense, right? Usually it's more easier to produce light particles, so why the constraint becomes weaker? Okay, so here's the reason, right? So basically, how to produce a dark photon? So because the only interaction between dark photon and photon is through this kinetic mixing. So any process which can produce a virtual photon basically can produce a dark photon, right? And now it is very easy to calculate the matrix element of this process. Okay, so there's a current and this matrix element of the current. And we know that this is the kinetic mixing term, and we can always integrate by part. And then because the dark photon, final dark photon is on shell, that means we can always use the equation motion, right, of this massive vector field. So then the kinetic mixing just, because dark photon is on shell, so just becomes a mass mixing, okay, becomes a mass mixing. So that means the matrix element is always proportional to MA prime square, okay? And we are not considering in the vacuum, we are in a plasma, right? We are producing dark photon in the plasma. So there is a plasma correction, okay, for the photon, for this photon propagator. Okay, so for the so what is this pi? It is actually the correlation function of the electromagnetic current in the plasma. Okay, this is the expectation value in the plasma. Okay, and for the transverse mode, what we have is that this pi t, this correction, so just equal to the plasma frequency square. And now from this formula, what you can see is that once the mass of the dark photon is much smaller than the plasma frequency, the production rate is just proportional to this epsilon kinetic mixing times MA prime square, right? So that's why the production, right? That's why the production for lighter dark photon becomes much smaller, right? So suppressed by the power to the fourth. What about for the longitudinal dark photon? For longitudinal dark photon, it is actually very interesting, okay? So basically, what you can show that if the mass of dark photon is very small, then we know that the polarization vector of the dark photon is just roughly proportional to the momentum, right? But if it is exactly the same as the momentum, then this product is just zero, right? Because the current is conserved, okay? So that means this pi L must be proportional to MA prime square, okay? Right? Because once MA prime goes to zero, it must go to zero. So now you can see that the MA square here just canceled, okay? But there's an additional MA prime from here. So that means for the production of the longitudinal dark photon, the matrix element always proportional to epsilon times MA prime, okay? And so then the production rate of longitudinal dark photon is proportional to MA prime square. So that is why we have this slope. We have the slope here, right? That's why we have the slope here. So for dark photon, production in thermal plasma, this is a quite general result. Okay, so now we can. So this is the result from this from the production of dark photon and inside the sun, right? This gives a constraint. So now we can compare it with the. So if the dark photon is heavier than 1 keV, okay, this is for lighter than 1 keV, okay, it can be produced inside the sun. But for heavier dark photon, it can be directly absorbed by the Xenon experiment. And this curve shows the current constraint. Of course, this red dot is, as Kai-Xuan mentioned, this is the best fit region for the Xenon 1-ton access. You can see that they're quite complementary to each other, right? So for heavier, you can just directly absorb it inside this experiment. But for the lighter part, you can produce it inside the sun. Okay, so now for the Higgs case, okay, so we just discussed Stueckelberg case. And we know that the production of Stueckelberg case is actually suppressed by the mass once the mass is very small. But for the Higgs case, because we have such an interaction, we have this interaction, right? It is very crucial, okay? Why it is crucial? Because with this cross section, we have the Higgs bremsstrahlung process, okay? So this is like Higgs-Strahlung process, okay? So basically through the dark photon, we can just emit a dark Higgs. If the mass of the Higgs and the mass of the dark photon is much smaller than the energy scale of this process, what we can use is the so-called Higgs effective theory, right? Basically, we can consider the emission of directly emission of this dark Higgs, direct production of the dark Higgs, and we know that this. So inside the thermal plasma, this is just like the massive transverse dark photon decay into a pair of dark Higgs. And so then this process is very similar, is equivalent actually to the case of producing light melee charged particles through a massive dark photon decay. Okay, and so you can see you can just from there you can have the experience that there's no suppression from MA prime. So that's why for this Higgs case, what you can show that for the Higgs case, all the constraints are just flat. Okay, are just flat. Okay, so now finishing talking about this producing dark photon at the center of the sun. So now let's talk about, now it's here, right? So basically from the previous slides, we already have this intuition, or we already have this concept in mind that the dark photon and the photon can oscillate into each other inside the thermal plasma, right? So that means that means to us, so how to search for dark photon, right? We just want to have a plasma, right? We want to find a large amount of plasma. And it turns out that the sun's atmosphere is just a vast source of plasma and also transparent, right? Because inside the plasma, what we showed previously is that inside the center of the sun, right? At the core of the sun, in the plasma, the photon can convert into dark photon, and dark photon fly outside the sun and then arrive Earth, right? But if the plasma itself is transparent to photon, then the dark photon, right? Then the dark photon can just resonantly convert into photon, and then photon can just maybe fly onto the surface of the Earth and be detected, right? And so this is the next. This is came out of our most recent work on to use the sun's atmosphere to detect dark photon, dark matter. So the idea is the following, right? So basically, as I show in this plot, right? So this is the distribution of the electron density. The green curve shows the distribution of the electron density, and we can see that so basically, if you convert the electron density to the plasma frequency, right? So basically, it's from 10 to the minus 4 EV at the chromosphere all the way to 10 to the minus 7 EV, right, at the corona. Okay, so basically, if the dark photon, if the mass of dark photon lie just in this region, right, in this region from 10 to the minus 4 EV to 10 to the minus 7 EV, it can just be resonantly converted into photon at the sun's atmosphere and then fly to Earth, right, and might be detected. But the condition is that it must be transparent, right? Okay, so basically we are going to study this. So what is the signal look like? The signal, what is the signal look like? So this resonant conversion means the plasma frequency equal to the mass of a dark photon. And we know that the inside dark matter halo, the velocity of the dark photon is actually very small, right? It is something like 10 to the minus 3, right? So that means the frequency of the converted photon, right, is roughly the same as the mass of the dark photon. And the dispersion is actually very small, right? It's about 10 to the minus 6. It is the kinetic energy of the kinetic energy of the dark photon, the dark matter, right? And so so then the signal of the converted photon is actually a monochromatic peak, very sharp peak in the solar spectrum. Okay, but to detect this signal, right, the material must be transparent for the photon to propagate to propagate to Earth, right? So there are basically two main processes to absorb photon. The most important one is the inverse bremsstrahlung effect, and so this is the formula. And we can see that due to this soft enhancement, so it is just a proportional inversely to the temperature, to the square root of the temperature, and also it is of course proportional to the number density of the nucleons and the number density, the ions, and also the number density of the electrons, right? So that means if the number density of the electron, we know these two numbers roughly equal to each other, right? So then that means if in this region, if the electron density is too large, then this most of the converted photon will be absorbed, okay? And so there will be no signal left. And it turns out that if the dark photon is converted into photon in the chromosphere, then most of the photons will be absorbed and we will have no signal. However, if this process happens if there's a conversion happen in corona, right, then because the low electron density and because the higher temperature, right, then this converted photon can just survive all the way to Earth, right, and be detected. And there's another process, which is the Compton scattering. The Compton scattering will shift the frequency of the converted photon, and then basically make this peak broader, right? And so basically we consider both the two processes as an absorption process, and we calculate this attenuation factor for the converted photon. Okay, and so what is the signal look like, right? So basically in this region, so basically in this region all around this corona. So the energy, the plasma frequency, right? So corresponding, if we translate it into the frequency of the photon, it is from in this part, in the boundary, it is about 1 gigahertz. And in this part, it's about 10 megahertz, right? So basically, we expect if the mass of the dark photon is in frequency is between 10 megahertz and 1 gigahertz, then it might be converted in the at the corona of the sun, and then be detected on Earth, right, by radio telescopes, right? So this is the illustration. So basically, you have a dark photon fly onto the atmosphere of the sun, and then become a photon, and then fly to Earth, be detected. Okay. So yeah. Okay, and so we did this analysis. So basically, for each radio telescope, there's a minimal detectable flux, which is defined in this way. You can see this. This is some efficiency factor, and this is the polarization number, which is 2 for photon, and this is the bandwidth, and this is the total observation time. Okay, and so this number is actually this SEFD is actually related to the noise, to the total noise, and the noise is contributed from this systematic temperature for the antenna, and also this effective area of the antenna, and also this is the noise from the sun. Okay, this is the noise from the sun. Basically, it is a temperature of the corona, which is something like 10 to the 6 Kelvin. Okay, and so this is a table of the parameters of this. These two, we basically did the analysis for these two telescopes. One is the SKA telescope at West Australia, and this is the LOFA telescope in Netherlands. And so basically, you can see that for the frequency range, the SKA can cover higher frequency, and this LOFA experiment basically can cover lower frequency. And so we did this analysis, and the results look like this. So this is our perspective limit, and we are just trying to interact with these people and trying to make these solid curves, to make these dashed curves to be solid curve, right? And if we are lucky enough, maybe we can find some signal there, right? And so here's the summary and the outlook. So basically, we know that dark matter exists, and we are eager to search for their particle natures, and also the sun as our own star can help us to search for them if they are light. And I basically discussed like 3 mechanisms. So one of them is for light dark matter. It can fly inside the sun and be accelerated by the electron inside the sun and fly to Earth, be detected. And the other is just to directly produce the dark photon dark matter at the center of the sun if the dark photon is lighter than 1 keV. And for even lighter dark matter, for radio frequency dark photon dark matter, it can be converted. It can be just converted at the atmosphere of the sun, right? And then fly to and convert it into radio waves, into monochromatic radio waves, and then this can fly to Earth and be detected. And so, but there are still a lot of things to do, because first of all, so we still don't fully understand the internal structure of the sun. For example, I think the most important one for particle physics is the magnetic field. And the current constraint for the magnetic field is that it should be smaller than about 10 to the 7 Gauss. And this is a very large number. And if this number is saturated, right, then the sun can just produce a lot of axions, right? And and so these people just did this analysis this year, very recently. Okay, did this analysis. They just show that then this production can be stronger than the Permkov effect, right? And also, so because we are looking for like plasmas, right? And we know that the atmosphere of the Earth has an ionosphere, right? So basically, in the ionosphere, it is basically a vast amount of plasma, right? And the plasma frequency is actually lower than the plasma frequency at the corona of the sun. So basically, it's at amhertz range. And so then if the dark photon mass is around amhertz, then maybe there it can just be converted into monochromatic radio wave and be detected, and somehow might be detected. And we already have the detectors, right? We know we have the long wavelength radios, right? They are basically detectors for these signals, right? But we also know that because of this, there must be a lot of noises. So basically, how to do this is still a question, right? So okay, so this is the end of my talk. Thank you for listening.
Okay. Yeah, thanks a lot for this illuminating talk. We have one online question. Maybe we can start with this one. So is there any effects on dark photon from the magnetic field in the sun?
No, the dark photon doesn't have because it's a pure mixing, right? So then the magnetic field doesn't, it's not very important for dark photon, but for axion it is important.
Okay.
Right? Yeah.
Hi, Paul. Nice talk. This is Xiaogang. I have one question. In the talk, you were arguing photon and the dark photon did not oscillate in vacuum. Okay, because you say, well, you have different dispersion relation.
Yes.
What about the neutrinos? Neutrinos, two different mass neutrinos, they also have a different dispersion relation, but they do oscillate in vacuum. So what's the difference?
Yeah, because you produce them in yeah, so the oscillation is I think it's a different language. It's a language in different bases, right?
No, if you, according to your theory, you produce it already have a mixing. Say for neutrinos, if they have
but somehow it must be virtual. It must be virtual.
Mass difference, they will oscillate. In the case you have is exactly the same thing. When you produce it, it's not in mass second state. It's in some fixed state. So then the branch out, it should have two states going in together. So I don't see that.